Hello, Algebra 2! Hope you guys are having a great day. Today we're going to talk about things you can do with complex numbers. So, operations. Your usual mathematical operations include multiplying, dividing, adding, and subtracting. Okay? We're also going to be graphing them and finding the absolute value of them. So, that's what our goal is today. Practice a little bit more with imaginary numbers. And yes, we are doing this out of order. We're doing 2.9 before 2.6 and 7 and 8, I think, because I thought it made more sense to do the two imaginary number problems together. Okay, so here we go. Graphing. Number 1, you gotta erase what you know about kind of parts of what you know about graphing a point, right? Typically, graphing, we have an x-axis and a y-axis, and then in order to plot something, you need an x-coordinate and a y-coordinate, and then you plot the point 2, you go over 2, and then up 3, okay? Those are the rules that we typically go by, right, when we're graphing. Now, it's different when you have a complex number, an imaginary number, right? And so you actually are on a completely different plane. This, the one that I have right here, is called the Cartesian plane. And the Cartesian plane, that's like the normal plane that we know about, the x-axis and the y-axis, okay? So when you're graphing imaginary numbers, you can't be on this plane because there is no place for imaginary numbers. So you start completely on a different plane. It's called the complex plane. And instead of having an x-axis and a y-axis, you have a real axis for the real part of the number and the imaginary axis for the imaginary part of the number. So I call the imaginary axis, I just write IM for short and RE for short for the real axis. Okay? So when you are graphing a complex number, you don't get two coordinates. You only get a single number. You graph a single number. So, for example, number 1, the number 2 minus 3i. Well, the real part is 2, right? That's this part here. The 2 is your real part. So you go to the right 2. You go right 2. And go, here we go, here's 1, here's 2, so I go to the right 2, and then minus 3i, I have to go down on the imaginary axis. So 1, 2, 3, that's the negative 3i part, so my point, 2 minus 3i, is right here. Now the next example, plotting the number -4 plus 0i, right? Well, your real part is -4. Okay, so you go over -4 on the real axis. So that's here, right? That's -4. And I have 0i. So my imaginary part is nothing. So my number is just on the real axis, right? Which is the same, it looks the same as the x-axis. It's not the x-axis, but it looks like the x-axis. Okay, so you should just go to the left 4 to plot that point. If you think you got it, you can try the next two on your own, check your answers. So pause. All right, number 3, 2i. There's no real part, so you only put a dot on the imaginary axis at positive 2i, which is right there. That's 2i. And then the last example is -1 plus 2i. So I go in, I go -1 on the real axis and up 2 on the imaginary axis. And that's how you graph imaginary and complex numbers on the complex plane. Good job! All right, absolute value of complex numbers. So it means the same thing as the absolute value of a normal real number. except you just calculate it differently, right? So the absolute value of a real number is just the distance from 0. So it's the same thing for complex numbers as well. The distance from 0 is what the absolute value represents. All right, so to find the distance from 0 for a point on the complex plane, right, you have to, well, one, figure out where 0 is. Where's 0? Same place it always is, right? It's right smack dab in the middle. So this is 0. And so anytime you have a point in the complex plane, to figure out the absolute value, you got to find the distance from 0. So for example, if my point was minus 3i, right, the distance from 0 is 3. Okay? If my point is 4 or negative 4, then my absolute value is 4, right? Because it's 4 away from 0. 1, 2, 3, 4, right? But it gets a little more complicated if it has a real part and an imaginary part, right? And you actually need the Pythagorean theorem for this. So let's try to find the absolute value of, let's try the number 1 minus 2i. Let's find the absolute value of that. All right, so you want to find the distance from that point to 0, which is here. So basically, you gotta, here's, that distance is 2, right? And this distance is 1. And then to find the absolute value, you need to find the distance between the point and 0. So you're trying to find the red, right? And that distance is if you create a 90-degree triangle, right? And this is A, and this is B, and this is C, then you've got the Pythagorean theorem, which is a squared plus b squared equals c squared, right? And so when you have that situation, then you can just solve for c by taking the square root of both sides, and then you end up with, well, plus or minus, but since it's a distance, then it doesn't matter. Distance always has to be positive. So anyways, in this case, a is 1, so we've got 1 squared plus, and then b is 2, so 2 squared, and that equals c squared, or the square root of that equals c. So we take the square root of 1 plus 4, square root of 5 is c. So the distance, right, the absolute value of 1 minus 2i is equal to the square root of 5, okay? And that would be your answer in this case. So algebraically, if you're trying to find the absolute value of a complex number, so you're trying to find the absolute value of a plus bi, right, that is equal to the square root of a squared plus b squared, okay? So, no I included, okay? You don't have an I in there. So that's kind of like your formula, but the Pythagorean theorem is where it comes from. So just so you have an idea of what that actually means and why that formula is what it is. So if you got that, go ahead, try the next couple examples. I'll talk through them kind of quickly, but so that you have an explanation. But so the absolute value of 3 plus 4i is just literally the square root of 3 squared plus 4 squared. Easy, right? So that's the square root of 9 plus 16. So square root of 25, which is just 5. So the absolute value of 3 plus 4i is 5. Yay! Next, square root of negative 2 plus I. Again, that is the square root of a, which is negative 2, squared. And then b is whatever's in front of I, and in this case, it's just 1. So we've got 1 squared. So you end up with the square root of 4 plus 1, which is the square root of 5. and that is the absolute value of negative 2 plus I. Operations, adding and subtracting is super easy. You just combine like terms. So in this case, we've got 3 plus 4i plus negative 2 plus I. So I'll simplify that a little bit. I've got 3 plus 4i, and then I'm adding negative 2 plus I. So my 3 and my negative 2 I can combine because those are like terms. So 3 plus negative 2 is 1, and then I can combine the 4i and the I, and that makes 5i, 1 plus 5i. Super easy. Same thing with subtraction, you just got to make sure that you're like paying attention to the negatives, right? So I've got 5 plus 2i minus 2 minus 3i, so that 5 plus 2i is here, and then that minus, you're subtracting that whole number, so that's minus 2, and you're also subtracting negative 3i, so that's minus a minus, which is plus 3i, and I can combine like terms. 5 minus 2 is 3, and then I've got that 2i plus 3i, which is, got a little bit of a delayed response here, which is plus 5i, okay? And so that is your final answer. Multiplying two complex numbers, again, it's kind of what you're used to, right? It's just foiling. But at the end, right, when you have an I times an I, you get I squared, which equals negative 1. So you want to simplify it as much as you possibly can. So in this case, I'm just going to write FOIL up here so you remember that you are just foiling. So you've got 3 times negative 2, which is negative 6. Then I've got 3 times I plus 3i. And then in the middle, I've got 4i times negative 2, so that's minus 8i. And then my last term is 4i times I, so that's 4i squared. So simplify that a bit. I've got negative 6, this 3i, and the minus 8i becomes negative 5i. 4i squared turns into 4 times negative 1, so that's minus 4. And then combine like terms again. So you've got negative 10 minus 5i. And then that is your final answer for multiplying two complex numbers. It's not too bad. All right, dividing is the one that gets a little more complicated, basically because you don't want to have a result that has an I in the denominator, and you don't want to be like dividing by an, well, yeah. You just don't want to have an I in the denominator, and that's essentially what your goal is when you divide complex numbers. So basically what I would do if you have a problem like this, 3 plus 4i divided by negative 2 plus I minus 2 plus I, you write it as a fraction first. Okay, step 1, write as a fraction. Step 2, multiply the top and bottom by the complex conjugate of the denominator, because that will get rid of the imaginary number in the denominator. So here I've kind of written your steps nicely. So step 2, multiply the numerator and denominator by the complex conjugate of the denominator. The denominator is negative 2 plus I. Remember, the complex conjugate changes the negatizes the imaginary part, right? So the complex conjugate of negative 2 plus I is negative 2 minus I. And then you just FOIL those out. You multiply straight across and simplify. So in this case, we start by multiplying across the numerator. So I've got that 3 times negative 2 is negative 6. 3 times negative I is negative 3i. 4i times negative 2 is negative 8i. And then the 4i times negative I is minus 4i squared. So that's the numerator. And the denominator, we want to do the same thing, FOIL. Negative 2 times negative 2 is positive 4. Negative 2 times negative I is plus 2i. Then minus 2i. then minus I squared, and then start reducing this. So, in the numerator, we have a negative 6, which can't combine with anything yet. You got negative 6. The minus 3i minus 8i is minus 11i. And then the minus 4i squared is 4 times negative 1 plus 4. So then I'll wait to combine those. Denominator is that 4 plus 2i minus 2i, those go away. And then I've got 4 minus negative 1, so that's 4 plus 1. Keep reducing. In the numerator, you have negative 6 plus 4, so that's negative 2 minus 11i, and that's all divided by 5. And so if we want to write it as in our typical form, a plus bi, then just write it as a fraction. So you've got negative 2 over 5 minus 11 over 5i. And then you have your answer. So yes, the division problems are much more difficult than the multiplication, addition, and subtraction. So we'll practice those a little bit more, but the key thing is remembering to multiply by the complex conjugate of the numerator of the denominator, because what that does is it gets rid of all the imaginary numbers in the denominator. So remember up here, like if you take a look at what the product was when we multiplied the conjugates together, right? The middle two terms, the 2i and the minus 2i, those cancel, and then this is always going to be an I squared term. So you always end up with a real number in the denominator. So it's nice. It's a nice way to simplify a complex problem. And that's it. Okay, bye-bye.